For this lesson, we are going to factor using what we call the fundamental theorem of algebra. And as we work through our lesson, actually what we're going to do is we're going to prove that the fundamental theorem of algebra actually works. And I will, or you will, factor polynomials to find their zeros. So this is very similar to what we did with our quadratics. Now we are just working now with the polynomials. So here's our fundamental theorem of algebra. Okay, over here. This is in your book on page 271 so that you can follow along. Let p of x be a polynomial function of degree n where n is greater than 0. The fundamental theorem of algebra states that p of x equal to 0 has at least one 0 in the complex number system. Let's recall when we learned about complex numbers. Remember that complex numbers appeared when we had a negative square root. And remember, our negative square roots came out as our little imaginary. So let's take a look. So we're going to find the zeros of the function 3x cubed plus 2x squared plus 6x plus 4. We're going to show that the fundamental theorem of algebra is true for this function by counting the number of zeros that we find. So remember, the fundamental theorem is stating that, in fact, we are going to end up with some imaginary numbers. So the first thing we're going to do is we're going to set our function equal to 0. So it will look like this. And then we're going to look for a factor common to all terms. We can use the quadratic trinomials formula, or we could factor by grouping. So if you notice that you have 4 terms here, first thing you're going to do is look for a greatest common factor. We have a 3, 2, 6, 4, so nothing there, and our x cannot come out. So with the 4 terms, we want to proceed with possibly our grouping. So let's take a look and let's factor. So let's factor out the binomials we want. So if we come up here, the 3x squared plus 2x, we'll group those together. So that means I will cover up my x here. So that means I'm going to factor out. I factor out an x squared, and that would leave me with a 3x plus 2. And let's see if we can get it to match over here on this side. Plus, I've got a 6x and a 4. If I factor out a 2, I have left a 3x plus 2. So now let's factor out our common factor of 3x plus 2. That leaves us with an x squared plus 2. I want to look at that x squared plus 2 very carefully to make sure that it cannot be factored any further. It is not a difference of 2 squares. It's an x squared, so it's not a cube. So therefore, we are done with this. Now our next step then is to set this equal to 0, just like we did with our quadratics, and then we will solve. So that gives me a 3x plus 2 equal to 0, and an x squared plus 2 equal to 0. We'll solve our first one here, so we would move our 2 to the other side as a negative, and then divide out our 3. So we have x equals negative 2/3 here. And then over here we have x squared plus 2 equal to 0. Well, I'm going to go ahead and move the 2 over as a negative 2. I have x squared equals negative 2. Now, if I want to go from an x squared to an x, all I have to do is its inverse and to take that root. So the root and square cancel, and I get x equal to the square root of negative 2. So now you can see where our theorem is working here. We know we cannot have a negative square root. So we're going to break that up. Remember, we break that up into the I times the 2, and the I will come out, or the negative 1, sorry. Let me erase all that and start over again. I'm going to break that into the negative 1 times the 2, and then our negative 1 is going to come out. So we would end up with the positive and negative I, because we brought him to the outside, and we still have the 2 under the radical, square root of 2. Remember, when we take square roots, remember your positive, negative. When we take square roots, we get the positive and the negative. So we had here a factor of 3, and we ended up with 3 zeros. Let's look at them. We ended up with the x equals negative 2/3 here, and over here we ended up with x plus or minus the I square root of 2. So in this case, we have 2 zeros here, we have 1 zero here, for a total of 3 zeros. 2 of those zeros being complex or imaginary. All right, let's take a look at A in our try these. Get out of there. So we have x to the 4th minus 16. So this is B. Let's take a look at that. Well, if I'm looking at that, I'm sitting here thinking maybe a difference of 2 squares. So that would give me, what could I square to get an x to the 4th? Let myself in room. And over here, what did I square to give me a 16? Well, to get to an x to the 4th, if I square that, and then my 16 would be the 4. So I'm going to drop that into my difference of 2 squares. My a being the x squared, my b being the 4, and remember we always have one positive and we have one negative. Now we're going to use our zero product theorem. We're going to set each of those equal to 0. And I look at the x squared minus 4, and actually, do you see something here? Do you see another difference of 2 squares? So we're going to actually factor that one again. So I'm going to take the x squared plus 4. I can't do anything with that one. I can, however, break this one down again. My a is going to be x. This time my b is going to be 2. One positive and one negative. Again, we are setting these equal to 0 so that we can solve them now. So my x squared plus 4 equals 0. My x minus my 2 equals 0. And my x plus 2 equals 0. These are easily solved. This one would give us the positive, and this one would give us the negative 2. Over here, we've got that square. So we're going to move our 4 over. So it would become negative. And we would have x squared equal to negative 4. And now we need our x, so we would take our square root. Our root and square cancel. X gives us the square root of negative 4. So again, we're bringing in our imaginary number. We would break that into negative 1 times the 4. Our negative 1 would come out as our I, and remember we will have plus and minus. But this time we do have a perfect square of 4, and 4 would come out as 2. So we would end up with plus or minus 2i. Now, we started with a power of 4, and as you can see, we do end up with 4 zeros. We have our 4 zeros here. You have 2 here, which is plus minus 2i. Here we have x equals 2 and x equals negative 2. So again, we have proved that that fundamental theorem is true because we did end up with complex numbers. Okay, now we're going to go back to A. Sorry about that. I zipped right over it. We're going to also use our zero product property to factor this one. So let's look at this one. We have an x cubed plus 9x What do you see here? Do we have a greatest common factor? I hope you said yes. They both contain the x, so we're going to take that out. That would leave us with an x squared plus 9. And x squared plus 9, we cannot do anything with either, so we're going to go ahead and set this equal to 0, use our zero product property. So we have x equal to 0, and we have x squared plus 9 equal to 0. So we'll solve this one here, basically what we did with our last one. The 9 will be moved over, so we would have x squared equals negative 9. And again, take our square root. We would get x equal to positive or negative square root. I'm going to break that up into the negative 1 times the 9. So our negative 1 is going to come out as the I. And then 9 again is a perfect square, and it's going to come out as 3. So that would give us x equals plus or minus 3i. This one had a power of 3, and you see that we end up with 3 zeros. We have a 0 here, 1 0, and we have 2 zeros here. Okay, we're going to look at one more. And this is D. And D is P of x equals x cubed minus 64. So I hope that you can look at that and figure out that that is a difference of cubes. So we're going to figure out what our A and B are. So I've got, what did I cube here, and what did I cube here? In this one, I cubed the x, and over here, I cubed the 4. So now we're going to put that into our formula, our binomial, and our trinomial. So our A, which is x, minus our B, which is 4. And on the inside, my A squared would be x squared. This is minus, so we change the sign to plus. Multiply those two together, we get a 4x, and then plus our B squared, which would be 4 squared, which is 16. So now we're going to set those equal to 0. The x squared plus 4x plus 16, we need to look at that. That one is not factorable by using the x method. So that one, we're going to introduce our quadratic formula. So we have our formula for a quadratic formula here, and now we're going to replace in our A, B, and C. So let's do that. So we would have negative 4 plus or minus, and there's that plus or minus again, our B squared, which would be 16, minus our 4 times our A of 1 times our C of 16, divided by our 2 times our A of 1. All right, now let's simplify all of that down. So we would have negative 4 plus or minus our 16 minus our 64 would give us a negative 48 under the radical over 2. And here in the negative 48, we're going to break that down into the negative 1 times our perfect square of 16 times our 3. So that will simplify down to negative 4 plus or minus. The 16 will come out as 4. The negative 1 will come out as I. We'll still leave our square root of 3 under, over 2. And now you can see that we can reduce the 4's and 2's. The 4's would become 2's, and the 2 would become 1, leaving us with a negative 2 plus or minus square root of 3. Okay. So again, we have over here, we'll finish this one. X minus 2 equals 0, so x would be the positive. So we have 1 0 here, and we have our other 2 zeros here. Again, proving that fundamental theorem that we will end up, whoops, I left off my I. Let me go back and add that in. Negative 2 plus or minus I, square root of 3. It gives us those other 2 for a total of 3. All right, so for your homework, you are going to work the check your understandings. You're going to work 1, 2, and 4, and you will bring those back to class. Again, those are on page 272. You are going to work 1, 2, and 4. And I will check those when you come to class.